Good morning, everyone, and welcome to this lecture on immittance parameters of multiport networks. I am Professor Farid Boutout from the Department of Telecommunications, Institute of Electronics and Telecommunications at the University of Borj-Barelej. In this lecture, we will develop the concepts of impedance and admittance parameters for multiport networks, derive their mathematical models, and interpret their physical significance in circuit and microwave engineering. By the end of this session, you should be able to derive immittance matrices for common two-port topologies, interpret each parameter physically, and prepare for the transition to scattering parameters. Let's begin by reviewing the evolution of network parameter representations and the motivation for immittance parameters. Before we begin the mathematical derivations, let me briefly present the organization of this lecture. The session is divided into two major parts, progressing from classical two-port networks to the general formulation for multiport microwave networks. Part 1. We first study immittance parameters of four fundamental two-port topologies: the T network, the series first L section, the shunt-first L section, and the pi network. For each topology, we derive both the impedance and admittance matrices and discuss their physical interpretation. Part 2. The second part extends these concepts to arbitrary n-port microwave networks. We introduce generalized voltage and current variables, establish the generalized immittance matrices, examine their important properties, and conclude by discussing the practical limitations of immittance parameters at microwave frequencies. Having established the roadmap of the lecture, we can now begin with the first network topology, the two-port T network. Before defining any parameter matrix, we establish consistent reference directions for voltages and currents. Both port currents are defined as entering the network, and voltage polarities are fixed. These conventions ensure compact matrix equations and prevent sign errors during derivations and parameter conversions. Maintaining these references throughout the analysis is essential for obtaining correct results. With the reference conventions established, we are ready to derive the impedance matrix. Now that the voltage and current reference conventions have been established, we are ready to define the first immittance representation of a two-port network, the impedance matrix, commonly referred to as the Z matrix. The impedance matrix establishes a linear relationship between the port voltages and the port currents. In other words, if the currents entering the two ports are known, the corresponding port voltages can be determined directly through the matrix equation shown on this slide. Each element of the matrix has a clear physical interpretation. The diagonal elements represent the driving point impedances, that is, the impedances observed when looking into each port under the specified open circuit condition. On the other hand, the off-diagonal elements represent the transfer impedances, which quantify how the current entering one port influences the voltage appearing at the other port. An important observation is that the Z matrix completely characterizes any linear two-port network operating under open circuit conditions. Once the four impedance parameters have been determined, the electrical behavior of the network is fully specified with the framework of impedance parameters. Throughout the remainder of this section, we shall learn how these matrix elements are obtained from practical circuits and how they can be interpreted from both mathematical and physical points of view. Having introduced the impedance matrix in its general form, let's now examine the physical meaning and experimental determination of each individual impedance parameter. On this slide, we introduce the classical two-port T network composed of the series impedances Z1 and Z2 together with the shunt impedance Z3. This topology will be used to derive both the impedance and admittance matrices. We will apply the formal parameter definitions directly to this network so that every matrix element has a clear physical interpretation. Having identified the topology, we now derive the impedance matrix. We now evaluate each impedance parameter under the required open circuit condition. The driving point impedances include the corresponding series arm and the common shunt impedance, while the transfer impedance are both equal to Z3, demonstrating reciprocity. Collecting these four quantities yields the complete Z matrix. Next, we determine the admittance parameters using short circuit conditions. To calculate the admittance parameters, port 2 is short-circuited so that V2 equals 0. We introduce the intermediate node voltage and apply circuit analysis to determine Y11 and Y21. Repeating the procedure with port 1 short-circuited provides the remaining elements, leading to the complete admittance matrix. In the next slide, we present the complete Y matrix and discuss its properties. We begin by determining the input admittance Y11 with port 2 short-circuited so that V2 equals 0. Under this condition, the input impedance is the series impedance Z1 plus the parallel combination of Z2 and Z3. Taking the reciprocal of this equivalent impedance immediately gives Y11. To simplify the final expressions, we introduce the common denominator delta, which will appear in every element of the admittance matrix. Next, we derive Y22 and the transfer admittance Y21. The quantity delta is defined as Z1 times Z2 plus Z1 times Z3 plus Z2 times Z3. By symmetry, Y22 is obtained directly by interchanging Z1 and Z2 in the expression for Y11. To evaluate Y21, we apply the formal definition under the condition V2 equals 0. The intermediate node voltage is first determined using the voltage divider rule before computing the output current. Using the intermediate node voltage, we now complete the derivation of Y21. The output current is related to the intermediate node voltage through impedance Z2. Substituting the voltage divider result into the current expression leads to the compact result Y21 equals minus Z3 divided by delta. The negative sign reflects the adopted current referential directions. We now repeat the same procedure from the opposite port to obtain Y12. To determine Y12, port 1 is now short-circuited so that V1 equals 0. This configuration is the dual of the previous one. The same analytical approach is applied. Determine the intermediate node voltage, evaluate the input current, and obtain the transfer admittance. The remaining transfer parameter Y12 is now obtained. Proceeding exactly as for Y21, we express the input current in terms of the intermediate node voltage and apply the voltage divider relationship. The resulting transfer admittance is Y12 equals minus Z3 divided by delta. Since Y12 equals Y21, the network satisfies the reciprocity property. We can now assemble all four admittance parameters into the complete Y matrix. Having derived all four admittance parameters individually, we collect them into the complete admittance matrix. The diagonal elements are the driving point admittances, while the off-diagonal elements are the transfer admittances. The common denominator delta appears in every element, providing a compact matrix representation of the T-network. This matrix completely characterizes the network in the admittance domain. Next, we apply these concepts to other two-port topologies. This slide introduces the series-first L-section network as a special case of the T-network. By setting the right-hand series impedance to 0, the T-network simplifies to an L-shaped topology containing one series impedance ZS and one shunt impedance ZP. Rather than deriving new formulas from scratch, we exploit the general T-network results through an appropriate parameter substitution. We now obtain the corresponding impedance and admittance matrices. Substituting Z2 equals 0, Z1 equals ZS, and Z3 equals ZP into the previously derived T-network expressions immediately yields the immittance matrices of the series-first L section. This illustrates the power of starting from a general topology. Many useful networks are obtained simply by specialization. Observe the physical meaning of the diagonal and transfer terms in both matrices. Next, we examine the complementary shunt-first L section. The shunt-first L section is obtained by setting the left-hand series impedance to 0 while keeping the right-hand series impedance equals to ZS and the shunt branch equals to ZP. The topology is therefore the mirror image of the previous L section, and we again use the general T network as the starting point. Applying the substitutions gives the corresponding Z and Y matrices. Replacing the T network parameters with Z1 equals 0, Z2 equals ZS, and Z3 equals ZP produces the impedance and admittance matrices of the shunt-first L section. Comparing these matrices with those of the series-first configuration highlights how exchanging the position of the series branch modifies the diagonal terms while preserving the overall analytical structure. The next topic extends the same methodology to other fundamental two-port topologies. This slide introduces the pi network, another fundamental two-port topology. Unlike the T network, the pi network is naturally described by admittance parameters because its shunt branches make nodal analysis straightforward. Nevertheless, both the admittance and impedance matrices can be obtained, and each provides a complete characterization of the network. We begin by deriving the impedance parameters from their formal definitions. To determine the impedance parameters, port 2 is left open so that I2 equals 0. Under this condition, we evaluate the driving point impedance Z11 and the transfer impedance Z21 directly from their definitions. We first derive the driving point impedance Z11. With port 2 open, the input impedance is the parallel combination of Z1 and the series path formed by Z2 and Z3. After expressing the result in terms of the admittances, we obtain a compact expression involving the common denominator delta, which will appear throughout the impedance matrix. Next, we determine the transfer impedance Z21. The transfer impedance is obtained from the voltage divider relationship between the intermediate branch and the output port. Combining this result with the previously derived expression for Z11 yields a simple expression for Z21 in terms of Y3 and delta. By symmetry, we immediately obtain the remaining impedance parameters. Using the symmetry of the pi network, Z22 and Z12 are obtained without repeating the full derivation. Collecting the four parameters produces the complete impedance matrix, which provides a compact mathematical description of the network. We now derive the admittance matrix directly from Kirchhoff's current law. The admittance matrix follows naturally from nodal analysis. Applying Kirchhoff's current law at each port gives two linear equations relating the currents and voltages. Rearranging these equations reveals the coefficients of the admittance matrix directly. Finally, we identify the matrix coefficients. Comparing the nodal equations with the standard matrix form allows us to identify each element of the admittance matrix immediately. The diagonal elements are the driving point admittances, while the off-diagonal elements are the negative transfer admittances. This completes the immittance characterization of the pi network. The next section applies these parameter matrices to practical examples and network analysis. Having completed the study of two-port networks, we now extend these concepts to the more general case of an arbitrary n-port microwave network. Many practical microwave systems, such as antenna arrays, filters, power dividers, multiplexers, and microwave integrated circuits, contain more than two ports. Rather than developing a different theory for each configuration, we introduce a unified mathematical description that applies regardless of the number of ports. At every port, two traveling waves coexist. The incident wave propagates toward the network, while the reflected wave propagates away from it. These waves will later become the foundation of scattering parameters. For the moment, however, we shall continue using equivalent voltages and currents, allowing us to extend the familiar impedance and admittance formulations to any number of ports. Having introduced the general n-port model, let's define the equivalent terminal voltages and currents associated with each port. For every port, we define two sets of variables. The first corresponds to the incident wave characterized by the equivalent voltage Vn plus and current In plus. The second corresponds to the reflected wave characterized by Vn minus and In minus. The actual terminal quantities are then obtained by combining these two contributions. The terminal voltage is simply the sum of the incident and reflected voltages. The terminal current is obtained as the difference between the incident and reflected currents according to the adopted reference direction. These equivalent variables provide the bridge between conventional circuit theory and traveling wave analysis used in microwave engineering. Using these equivalent voltages and currents, we can now establish the generalized mathematical description of an arbitrary n-port network. Just as for two-port networks, an arbitrary n-port network may be represented in two equivalent ways. The first representation uses the impedance matrix, which relates the voltage vector to the current vector. The second uses the admittance matrix, which expresses the current vector as a function of the voltage vector. Notice that the vectors now contain n components, one for each port of the network. Therefore, these equations remain identical in form to those already studied for two-port networks. Only the matrix dimension changes. This unified notation allows the same mathematical tools to be applied to networks containing any number of ports. Having introduced the vector equations, we can now examine the structure of the generalized impedance and admittance matrices. The generalized impedance and admittance matrices are square matrices of order n. Each element describes the electrical interaction between two ports. A diagonal element represents the driving point behavior of a port, whereas an off-diagonal element represents the coupling between two different ports. Since both matrices describe exactly the same physical network, they are mathematical inverses of one another whenever the inverse exists. Consequently, when either the impedance matrix or the admittance matrix is known, the other may be obtained directly through matrix inversion. This relationship concludes the general formulation of immittance matrices before we proceed to define the meaning of every individual matrix element. In the next slides, we shall define each impedance and admittance parameter individually and explain the experimental conditions required for their measurement. In the previous section, we derived the impedance and admittance matrices for specific two-port circuits. We now generalize these definitions to an arbitrary n-port network. The impedance parameter Zij is defined as the ratio of the voltage measured at port A to the current injected into port J, while every other port is open-circuited. In other words, all currents except the excitation current are equal to 0. Similarly, the admittance parameter Yij is defined as the ratio of the current measured at port I to the voltage applied at port J, while every other port is short-circuited, meaning that all the remaining port voltages are 0. These definitions provide the foundation for constructing the impedance and admittance matrices of any linear multiport network. This slide explains how an impedance parameter is measured in practice. To determine the element Zij, we inject a current into port J while ensuring that every other port is left open-circuited. The voltage that appears at port I is then measured. The ratio of this measured voltage to the injected current gives the impedance parameter Zij. This experimental viewpoint makes the mathematical definition much easier to understand. The impedance parameters have two distinct physical meanings. When the row and column indices are identical, the element Zii is called the driving point or input impedance. It represents the impedance seen when looking into port I, while every other port remains open-circuited. When the indices are different, the element Zij is called the transfer impedance. It quantifies how the current injected into one port influences the voltage measured at another port. Therefore, the diagonal elements describe the behavior of individual ports, whereas the off-diagonal elements describe the coupling between different ports. Physical interpretation of the admittance parameters. The measurement procedure for admittance parameters is dual to that of impedance parameters. Instead of exciting the network with a current source, we apply a voltage source to port J. Every remaining port is short-circuited so that its voltage is zero. We then measure the current flowing at port I. The ratio of the measured current to the applied voltage defines the admittance parameter Yij. Driving points and transfer admittances. The interpretation follows exactly the same logic as for the impedance matrix. The diagonal elements Yii represent the driving point admittances observed at each port under short-circuit conditions. The off-diagonal elements Yij represent the transfer admittances that describe how a voltage applied at one port produces a current at another port. Again, the diagonal terms characterize individual ports, while the off-diagonal terms characterize the interaction between ports. Properties of generalized immittance matrices. We now summarize the main properties of impedance and admittance matrices. For an arbitrary n-port network, both matrices are square matrices of order n containing n2 complex elements. Many practical microwave networks are reciprocal. For reciprocal networks, the matrices are symmetric, meaning that Zij equals to Zji and Yij equals to Yji. If the network is lossless, every impedance and admittance parameter is purely imaginary, since the real parts are equal to zero. These properties are extremely useful because they simplify both analysis and network characterization. Limitations of immittance parameters. Although impedance and admittance parameters are mathematically convenient, they became difficult to measure at microwave frequencies. The determination of impedance parameters requires ideal open circuits, whereas admittance parameters require ideal short circuits. At high frequencies, these determinations are difficult to realize because they introduce radiation, parasitic effects, oscillations, and measurement inaccuracies. For this reason, microwave engineering relies instead on incident and reflected traveling waves. This naturally leads to the definition of scattering parameters, which form the basis of modern microwave network analysis and will be introduced in the next section.